Hello, everyone. My name is Ziyi Chen, and today I'm going to present literature review on electrostatic discharge device protection. The outline of my presentation is as follows. First part is introduction to ESD protection. The second part is about challenges and trends for ESD protection. And third part is about existing techniques for ESD protection. And the final part is about conclusion. So let's first start from the ESD protection for CMOS VLSI, or ESD stress on input and output pins. So in these stress modes, we can have 4 different locations of ESD stress, which applied on VDD pin, on VSS pin, on input pin, or on the output pin. And there are also two polarity of ESD voltage, positive or negative. So you can see that we actually have 4 modes of ESD stresses: the PS mode, or the positive voltage applied on a VSS pin, or NS mode, a negative VSD voltage applied on a VSS pin, or a PD mode, a positive voltage applied to a VDD pin, or ND mode, and negative voltage applied to a VDD pin. Also, we can have 2 additional modes for ESD protection. The first one is pin-to-pin ESD stress. So ESD voltage is pressed on a single pin, with other input pin and output pins grounded. And the VSS VDD pins is floating. And the second stress is VDD to VSS ESD stress. So in this condition, the ESD voltage is applied to VDD pin, with input and output pins floating in these cases, and the VS pins is grounded. So you can see on the right side, we have also 4 different apply mode: the positive mode, negative mode, apply either to single input pin or on VDD pin. In this slide, I'm going to discuss about the ESD current pass through the IC under the pin-to-pin ESD testing condition. So the positive ESD voltage is applied on partial input pins, with our output pins grounded in this condition. Our VDD and VSS pins are floating. So you can see that when voltage, assuming a positive voltage comes from the voltage source on the left side, goes into the input pad and a serial resistance passing through the diode DP1. And that current flows into the power rail. Recall that the power rail is actually connected to the internal IC. The ESD current flows through the internal IC and damage the device. And similarly, we can apply a negative ESD voltage on partial output pins. So we will see a negative voltage source on output, and a current flows from the ground rail of VSS through the diode on the bottom, all the way to the output pad and into the negative voltage source. So in this case, output pins is grounded, and the VDD and the VSS pins is floating. So you can see the difference between the two is that we apply a positive voltage on the input pad, or we applied a negative voltage on the output pad. And the ESD current is flowing through the diode on the top to the VDD when we apply a positive voltage, or the ESD current is passing through the diode on the bottom to the output pad when we apply a negative voltage. Next, I'm going to discuss the VDD to VSS ESD stress condition. So the internal circuit is sensitive to ESD current due to the fact that the layout is small comparing to the overall IC. Knowing that in addition to internal core design, we also have other peripheral circuits. So the overall area of the chip will be much larger than that of the internal circuits. So that the internal IC is pretty sensitive to the ESD current, which is relatively large. And it's also hard to measure the ESD current of the internal circuits because the area of that layout is too small to be spotted. Next, I'm going to discuss the ESD clamp device. You can see that on the right side is a NMOS ESD clamp device with the gate grounded, so that the ESD voltage is clamped by the NMOS. And with the gate voltage grounded, the NMOS can be broken down by the ESD stress and the passing ESD current. And the small IC has a small sizes and is placed actually on the left side of this clamp device. So in this case, if we assume we have an ESD current passing through the input pad on the left side, all the way to the DP1 to the VDD, the stress may not be sufficiently relieved, and a large current can still be applied to the internal circuits because the current needs to travel a long ways to the power rail to the NMOS device on the right side. So the location of our ESD clamp device is very important. And the internal IC is prone to be damaged before the NMOS release the ESD stress in this typically schematic. So we want to investigate the power line delay. Recall that the power line of an IC could be a long rail. If we have a voltage applied on the one side of a power rail, and if we put the clamp device too far from the internal ICs, then the overall current goes into the IC could still be pretty large. This is called the discharge delay due to long power rail. And the ESD stress pin is also spacing dependent, depend on what pin we want to see the ESD stress. For example, if our input pad is put on the left side and our clamp device on the right side, then this is the worst case delay. However, if our input pad is like put in the middle, so that the distance traveled to the ESD clamp device will be much smaller. So next, we are going to study the location of our input pad, which we will discuss that on the power line delay. However, let's first take a look at the protection in the analog circuit. So for analog and RFIC, which is bandwidth sensitive, we want to assure that we have a maximum bandwidth after we have added our ESD clamp device. So in this example, we have a ESD protection with a grounded pad put in the center of our chip. Assisted by the transmitter switches, the BJT can turn on by a ESD voltage, and the ESD current discharged through the power amplifier ground pad. So in this example, we want to maximize our bandwidth, and we also want to meet the insertion loss requirement and impedance matching requirements, which we will discuss in detail later. Okay, now let's take a look at the power line delay. So the power line delay depend on the location of our input and output paths. So in this test condition, we put our output pad on the left side and our input pad on the right side. And we have a ESD clamp device located below our VDD pad, so that you can see if we apply ESD stress on different pads, we can measure the voltage seen on the ESD clamp. And we can generate the rules that how much delay is introduced by the power rail. And we can also do the same thing for the input pad and see what will be the delay from the input pad and measure the voltage level seen on the ESD clamp device. Now let's take a look at the high-speed ESD protection circuits criteria in the analog domain. So analog domain requires wide bandwidth, and we have also to deal with the effects of parasitic capacitance from the ESD device, which means that the ESD device should be as small as possible. And we want to present the impedance matching at the input and output pins. And we also want to avoid any signal loss, which is very important in transmitter and receiver. Let's first take a look at the efficient VDD to VSS ESD clamp device in CMOS VLSI. So this is a typical design of a ESD clamp device. The operation can be described as follows. We first detect a transient current flow through VDD to VSS. And this will turn on the sensing transistors. And this transistor will remain off on the normal condition. Next, let's take a look how this works in detail. So the operation can be described as follows. First, power pins remains floating. And when we begin to test the IC, a ESD stress is applied on VDD. So initially, Vx and Vg share the same voltage level due to the fact that both power rails are floating, and the voltage of these two are ground. And after we apply a ESD stress, it will charge the capacitance C to a voltage level. Let's assume it to be Vx. However, the voltage increasing on the capacitance node is much slower than that on the power rail because of the RC delay. So we can see that the voltage on the source of this PMOSFET MP will be large than that of the voltage of Vx, so that we can turn on the PMOSFET due to the fact that the gate voltage level is lower than the source voltage level by one threshold voltage. So after we turn on MP, Vg is charged to the ESD stress voltage, and the gate voltage of this NMOS will be larger than the threshold. So we turn on this NMOS, and the ESD current passing through the NMOS. Hence, we release the ESD current from the VDD through this NMOS. Now let's take a look at the conventional circuit technology for ESD protection in analog domain. This is a typical example of an analog RC model. The CESD represents the parasitic introduced by the ESD clamp device. And we have a input voltage source Vin, we have a serial resistance Rs, we have a common source input M1. So the bandwidth of signal is limited by the ESD parasitic capacitance. So it's necessary to minimize the impact of ESD parasitic on input and output port. One technique is to using inductive peaking, making the signal bandwidth wider. This can be done by resonating out the parasitic using the inductance. And it can be assisted by serial resistance on the input port. However, inductive peaking suffering from poor impedance matching. And in this example, we also test the S11 or the reflection on the input node. We want the reflection as small as possible. So in the simulation result, it shows a minus 10 dB reflection at 2.4 gigahertz. If we want the reflection to be as small as possible, we have to make our input frequency smaller, indicating that our signal bandwidth is limited within 2.4 gigahertz. We can also model the ESD parasitic using distributed model. The CESD is the total ESD capacitance. And we can using transmission line to obtain a 50 ohm input impedance. Using the formula below, we can change the length of our transmission line. And if we predict the parasitic of ESD and the parasitic capacitance of our transmission line, we can obtain a purely 50 ohm input impedance by tuning the length of transmission line. Now let's take a look at the broadband ESD protection circuit in CMOS technology. In this technology, we using T coils to resonate out parasitic capacitance. So the T coils has two merits. The first one is the purely resistive input impedance that can be achieved by resonating out the parasitic capacitance. And the bandwidth is wider than that of inductive peaking. And the transfer function is given below. If we study the location of the poles, we can see that both poles lies in the left half plane, indicating this is a stable system. T-coils can also be applied to differential circuit by just placing another T-coils on the right side. So assuming we have a differential pair in the middle, and we have two input differential paths. So let's assume the left side is a positive input and the right side is a negative input. Both paths has a T-coil to resonate out the parasitic capacitance of our ESD clamp device. In this typical example, L1 and L2 equals 1 nanohenry, and it's assuming a 50 ohm output load. Now let's take a look at the ESD in RF system. So RF circuits is more sensitive to ESD stress due to the fact that the RF signal is often operating in high frequency. And the LNA is the first stage receiving RF signal and is directly exposed to ESD stress. So it's very challenging to deploy ESD protection without harming the RF performance. In this example, we use an inductor embedded within ESD protection circuits so that we can make the LNA design remains unchanged, and we just need to deal with the ESD protection device. And we assume an LNA common source input stage with a 50 ohm impedance matching. By remaining the LNA design unchanged, the design of the overall IC is easier. So we just need to tune the inductance within our ESD protection circuit. And this is the simulation results indicating the gate voltage of M1 or the input transistor. The x-axis is the time. And the y-axis on the left side is the gate voltage of M1. And the y-axis on the right side is HBM current. So HBM is called human body measurement, and it provides a current, simulate a current from the human body to the overall IC. You can see that if we have a current flowing through the IC, it will cause a, which represented by the dotted line, it will generate a overshoot. The solid line represents the input voltage on the gate. And you can see that the solid line has an overshoot due to the HBM current. So the gate of M1 is sensitive to ESD stress. And the HBM simulation indicates we should protect the ESD from the human body current. We can also model the input port into a small signal model with a voltage source on the left side and a serial resistance. We also have a inductance of ESD and the resistance of ESD. And we also take considered of a parasitic capacitance and the parasitic capacitance of differential pair. So that the ultimate goal is to resonate out all parasitic capacitance. And we find that the input matching is guaranteed with the parallel ESD much greater than 50 ohm. So if we calculate the parallel resistance of ESD by the following formula, we find that it's frequency dependent. So we can first determine our targeted frequency, and then we can tune the ratio between R and L. Now let's take a look at the inductance selection. So the input reflection is also one important metric in RFIC. And for example, if we want input reflection to be smaller than -10 dB, then we can draw a horizontal line in the graph. And also we want to determine our operating frequency. So for example, if our frequency is set to be 6 gigahertz, and we find that the inductance with 1 nanohenry is much smaller, it's smaller than -10 dB reflection. Hence, 1 nanohenry will be optimal. So you can see that this is also frequency dependent, and we simulate with 1 nanohenry inductance to 5 nanohenry inductance. And now let's take a look at the gate voltage simulation. So recall that HBM, or human body measurement, is a metric of ESD. Human body discharging through an electrical device to the ground. So in this measurement, we can see that when our inductance of ESD is 5 nanohenry, the HBM analysis shows 4-volt stress on the gate voltage, which is close to the minimal gate breakdown voltage. So we should be very careful to choose our inductance to make sure our HBM voltage remains far below the breakdown voltage of our gates. And another important metric in RFIC is called the noise figure. So typically for LNA, we require noise figure to be lower than 3 dB. And this is a simulation with different inductance of ESD circuits. So you can see that if we draw a horizontal line, a 3 dB noise figure, and we want to determine the operating frequency, for example, between 4 gigahertz to 6 gigahertz, so that we can only choose inductance with 3 nanohenry or inductance with 5 nanohenry. So these two inductance meet our requirement to maintain our noise figure below 3 dB, where our operating frequency is between 4 and 6 gigahertz. So in this typical design, we choose 3 nanohenry inductance. Finally, let's conclude the ESD protection. So the key rules of ESD protection is prevent the voltage on the inputs or output port from rising too high that will damage the internal circuit. ESD protection device can be implemented as a single NMOS in digital design, or it can also be implemented using inductance to resonate out parasitic in analog or RF design. In CMOS VLSI, long power rail will cause a delay on ESD stretch voltage. And in RF design, impedance matching need to be considered along with ESD design. Inductors can resonate out parasitic capacitance, enhancing signal bandwidth in RF IC protection. That's all my presentation. Thank you for watching.